but we have that theorem. This is the absolute highlight of calculus, is that beautiful theorem which says that if we integrate from 0 to x, and then we take the derivative of t in t, we get that this is equal to f of x minus f of 0. So that's one part of the fundamental theorem. We have already seen that in the discrete case. And then there is another theorem which says if you differentiate the integral f of t dt, what is the result? F of x. That's f of x. So there are two parts of this fundamental theorem of calculus, and one part says that if we integrate the derivative, we get essentially the function back, a constant, and if we differentiate the integral, we get the function back. So this is the fundamental theorem of calculus, maybe abbreviated just fundamental theorem of calculus. And I want to prove this a little bit differently than on the handout today. So this tells that integration reverses differentiation. Remember, we have seen that in the first week. We have seen that already. We have seen that S of d of f was actually just, that was here, that was f of x. That was f of x minus f of 0. And then we have the d of s of f x is equal to f of x, where d was the discrete derivative and s was the discrete summation. And that's just now the version with the real derivative. So we have a derivative and we have an integral, and when you integrate the derivative, you get the function back. When you take the derivative of the integral, you get the function back. So it's an absolutely fantastic theorem. And I want to just draw two pictures which proves this. Two pictures. So the first picture is here. So let's just see what this actually means. Let me just draw a graph here, and then the second one is also for the second part. So this is x. And what we do here is we take a function and we take the slope of the function and integrate that up. So let me just make a little kind of picture here. So I make a discrete part and say this is the function which we kind of assume to be piecewise linear, maybe something like that. So this is a kind of a discrete version of a function, and that's x here, and that's 0. So that's f of 0. That's the graph of the function f, and that's f of 0, and that's f of x here. And if you look at when you look at this picture here, what we have is fx minus f0 is actually just this difference here. Right? This is this difference here. Fx. This is fx minus f0. That's the gain. We have the total gain, which we have is the total change of the value. If this is a stock market price, then this is just the total gain we have over from 0 to x. But what we have here is a sum of rate of change. So f prime t is a slope. So if this is equal to d, let me just make one picture here. So what actually happens here, if this is dx, I just write here dx here, and if this is dx, then this is right over run is the slope, right? We get actually just that this is f prime x dx, or t, dt. So what this result says, let me just give you the picture. What this result says that if we add up all these rate of changes, so this is the rate of change going from here to here, we add up the rate of change going from here to here, we add up the rate of change here, we add up all, here we lose something, we are losing something, and so we add up all these rate of changes. Then what we do is we add up all these green parts here. What happens is we get the total gain. So it is a very intuitive result. The total rate of change is just the total. This is the difference between the end point and the initial point. So that's one picture. And the second picture is similar. So what we have is this can be interpreted as an area. So let's just take an area here. This is the area here. So let's just write here. This is the integral from 0 to x f of t dt. It's an area. So we have an area. And what we do is we take the rate of change of this area when x goes from x to so here x. And then maybe here is x plus dx, or x plus h. So what happens is that the function has kind of changed a little bit. But what happens is, if you look at this part, and you have done that for today, and see when you take the integral from here to here minus the integral from here to here, you get that area here. So that area is actually just the integral. Let me just write it with a capital F. So that's actually just f of x. So then I don't have to write the integral again. So this what we have here, this orange area, is nothing else than f of x plus bx minus f of x. Right? F is the capital F is the area going from 0 to x. So we take the area from 0 to x plus dx and subtract the area, the yellow area, we get this. And what happens if we divide by dx, right? If we divide here by dx, by the base, we get the area divided by the base length. What does that give us essentially? This is a rectangle. In a rectangle, and what is the value of that? What is the height of that rectangle?
X plus d minus x.
So what is the value here? So this is the function f of x. What is the value of that height here? Essentially f of x. Essentially f of x. So if we divide by dx, we get essentially. Make sense? So that's the picture. So if you have these pictures in mind, it should be clear why you get f of x, and not f of x minus f of 0 here, but here you get f of x minus f of 0 because you have the gain from f of 0 to f of x. So in the handout you have a little bit more algebraic proof using this discrete word, but I think this is very good. Yeah. Questions? So that's the theory for today. I think that's the highlight of calculus. And you only really appreciate it when you start solving problems like you have done for today. I know this has been a little bit some of the problems have been a little bit tough, so because this lecture had not been here. But what I want to do is, I actually just want to do a couple of examples and then talk about antiderivatives and then force you to learn a few antiderivatives and tell you a little bit about techniques, how to memorize things. So let's look at the examples. We've already looked at the examples last time, but let me just, again. So one of the kind of nice examples, which would be hard to do by Riemann sum, is to take the sine function, f of x is equal to sine x. And we want to integrate from, we want to compute this area here. So this is 1, and we have here pi, 0 to pi. What is this integral from 0 to pi sinus x dx? So that would be hard to do by any type of Riemann sum. You would have to sum up only sine of, k over n values, which would be hard. But what we can do is we can say, okay, which function gives us the area from 0 to x? Right? If you compute the area from 0 to x under the curve, what we get is just the antiderivative here. So this area here is actually just, we need a function f of x. Usually we call this f of x here, such that its derivative is small f of x. So we need an f such that f prime of x is equal to f of x, which is equal to sinus of x. Now we have already kind of a list of functions which we know how to differentiate. So in this case, what function gives us the sine of x when we differentiate? Cosine, yeah, but negative cosine of x. So we kind of just by knowing d over dx of cosine x is minus sinus x, we see that f of x is actually this minus cosine x. So what we can do is now we can use this theorem and say, okay, we can actually use it here. So this f prime here was the sine of x. So f of x is equal to minus cosine x. So that's minus cosine x. And then we evaluate it. Usually we write it like that. We take a horizontal, a vertical line here, and then we go from 0 to pi. So this means we evaluate it at pi, and then we subtract what happens at 0. So this is minus cosine pi, minus plus cosine 0. And cosine pi, we know, is equal to minus 1. So that's 1 plus 1 is equal to 2. Does it make sense?
Yes.
Very prototypical example. Sometimes it's a little bit hard to come up with an antiderivative. Say, for example, if you have something like integral from 0 to 1 of 1 plus x to the 5/2. So you have done something similar than that for today. That looks already tough, right? So it's the square root of 1 plus x to the 5. So this looks complicated. The square root of 1 plus x to the 5. That's looks like a tough integral. But we know something about functions which are of the form x to the n. And whether you have 1 plus x to the n or x to the n, it doesn't really matter. What we know is f Let's just see, does somebody know what is the antiderivative here just off the bat? 2 sevens times?
1 plus x, that, or 2 7 half.
Very good, very good. Yeah, you already approach, so that's kind of what we do. So we know when we take the derivative of, that's kind of the most important identity, x to the n. It doesn't matter whether n is an integer or a fraction or a real number. So that's equal to n times x to the n minus 1. It's one of the basic identities we have seen when we differentiate. And now we can reverse this. And if we reverse this, we see that if we want to go from x to the n minus 1 to the integral, so this is the derivative, this is the f, and this is the capital F. This is the capital F. If you want to go from the small f to the big F, what we have to do is we have to take that power and add 1 and then divide by that number. So, and that's kind of the important identity. If you take the x to the n dx, so what you get is x to the n plus 1. We go up 1, so we add 1, and then a little bit kind of strangely, we don't divide by n, but we divide by n plus 1. And so that's so this is one of the identities we really have. So in this case, we have n is equal to 5/2. We just do that quickly. And with 5/2, so 5 is the integral from 0 to 1 of 1 plus x to the 5/2 dx. So that's our n here. That n gets increased by 1. So that's 1 plus x to the 1 plus 5/2, which is 7/2. And then we divide by 7/2. We divide by n. So that means multiplying by 2 sevens. And then we evaluate it from 0 to 1. So that's just 2 sevens. And then we have 1 plus 1 to the 7/2 minus 1 to the 7/2. And I think you have done a very similar example in the homework. That's just 2 to the 7, so that's 2 over 7. 2 to the 7 is, actually that won't be right. Now it should be clear. What happens here is because we have this 1 plus x. It's not x to the 5/2, but 1 plus x to the 5/2. But it doesn't really matter because when you take the derivative of that inner function, that's still 1. So we can do it for every a. So we can actually say the integral from 0 to x, a plus x to the n dx is still kind of a plus x to the n plus 1 over n plus 1. Pretty cool. What is this integral? Let me just make a third example here. The integral from 1 to 2, 1 over x dx. This deserves actually a separate page. It's very important. It's a very important case when n is equal to -1, right? So this is when n is equal to different from, so n is different from not equal to -1. That is the integral from 1 to 2, 1 over x dx. So there's the log coming out. The ln. is equal to ln 2, the log of 2, minus the log of 1. What is the log of 2? Number. What is the log of 1? 0. So that's actually just 2. It's a number a little bit smaller than 1.